Okay, so today we'll be going over exactness. There's a few things that we need to know before we can start doing examples. First off, standard form for exactness problems is m dx plus n dy is equal to 0. If the partial derivative of m with respect to y is equal to the partial derivative of n with respect to x, then the problem is exact. If and only if the problem is exact, we can continue to solve it, and the formula that we'll use to continue to solve it is this one. F of x comma y is equal to the integration of m dx plus g of y is equal to c1. And c1 in this formula is just a placeholder for c in case we forget to add a plus c after we integrate. Okay, now let's go ahead and start doing an example problem. Example 1, 8y cubed y prime equals 5x plus 4x y prime plus 4y. So in this case, we have two y primes. We need to make it so that we only have one before we can put this in standard form. So let's go ahead and put all of our y primes in the left side. So I'm going to go ahead and subtract 4x y prime equals 5x. 4y. Okay. So notice on the left side, both terms have a y prime. So we're going to go ahead and take out y prime. Like so. And now we're going to substitute that y prime in for dy dx, because y prime is equal to dy dx. So it's just rewriting this. 8 cubed minus 4x is equal to 5x plus 4y. Okay. We're going to multiply both sides by dx. dy cubed where x is equal to 5x plus 4y dx. Now, according to our standard form that we have here, we need everything to be on the left side, and also we need to have a plus sign between both terms. So let's go ahead and move everything to the left side. dy 8y cubed minus 4x minus 5x plus 4y dx is equal to 0. And we need this negative sign to become a plus sign. So what we can do is we can distribute it to this side and replace it by a plus sign, like this. Plus, and now everything in here becomes a negative. Like so. Okay, now this here now meets standard form, which means we can start checking for exactness. So if we look back at our standard form was m dx plus n dy is equal to 0. So the parentheses that's in front of our dx, which is here, is going to be our m, and the parentheses that is attached to our dy is going to be our n. So when we take the partial derivative with respect to the partial derivative of m with respect to y, we're going to be looking at this, and our independent variable is going to be our y, and everything else is going to be a constant. So this first part is going to be just a constant, so 0. And then the second part, which is this, actually has a y, so we take the derivative, we get minus 4. And then for n, we take the partial derivative of n with respect to x. And for the first part, because we're doing this with respect to x, all of it is a constant. There's no x. So 0 minus 4x. There's an independent variable x, so we take the derivative of it, we get minus 4. If we rewrite it, we get minus 4 for both, which means that the partial derivative of m with respect to y is equal to the partial derivative of n with respect to x, meaning that they are exact. Now that we've discovered that this equation is exact, we can continue on using this equation, f of x, y is equal to integration n x plus g y equals c1. Okay, so here we're going to plug in our m. So let me rewrite this. Integration of m, and our m is going to be our original m that we have here. So minus 5x minus 4y, integration with respect to dx, plus g of y equals c1. Okay, now our goal here is for us to find this g of y, but first we need to take the integration here. So f of x comma y, we take the integration with respect to dx, so minus 5x squared over 2 minus 4y x plus g of y equals c1. This here is the format of our final answer. From here on, all that we're trying to look for is the value of this. And in the end, we'll plug it back into this equation here. Okay. Now, from here, I'm going to go ahead and rewrite this. And I'm not going to carry on the c. This c here is just, again, as a placeholder to make sure that we don't forget to put plus c's. Because this is already included, I'm not going to put plus c's after we integrate. Minus 5x squared 2 minus 4yx plus gy is equal to f of x y. Now here, we're going to take the partial derivative of everything on both sides with respect to y. Okay, so our independent variable is y now, and anything else is treated as a constant. So all of this is a constant, so when we take the derivative, that becomes 0. This here is going to become minus 4x, and this gy is going to become dg dy, derivative g with respect to y, because we don't know exactly what our gy is. That's what we're looking for. And here, this gives us partial derivative of f with respect to y, which is equal to n. And n is equal to, we're talking about this n right here, 8y cubed minus 4x. So we're going to write 8y cubed minus 4x. Okay. So now if we rewrite this, minus 4x plus dg dy is equal to 8y cubed minus 4x. So notice that we have minus 4x on both sides. We can go ahead and cancel those. And we're going to go ahead and separate our dg and dy. So we're going to multiply both sides by dy, like this. And we're going to take the integration of both sides. Integration of dg here is going to be g, or you can write it as g of y. Either one is appropriate. So how do I get g from this? It's understood that there's an imaginary 1 here, so integration of 1 is just g. And then on the right side of the equation, we get 8y to the 4th divided by 4. So we have g is equal to, and now we can simplify this, which is 2y to the 4th. So we have our value of g, or gy, and our final answer is going to be this inputted into this equation here. So it's going to be, I'm going to write it all out at the very end here. So f of x, y is equal to negative 5x squared over 2 minus 4yx plus our gy, which is 2y to the 4th, is equal to c1. This here is going to be our final answer. If we had gotten that these weren't exact, we would have not moved on to doing this next step. So we can only move on to doing this next step if we get that the functions are exact. So can only move on if exact. If it's not exact, then we just say it's not exact and we leave it like that. This is how we solved exactness problems.